Welcome to Hartman Math. Today we're going to take a look at polynomial functions of higher degree, but before we get to that, a little warm-up that ties us back to lesson 2.1. Standard form equation for the parabola vertex at negative 2, 5 passes through 2, negative 3. A little sketch here where we've got a barn and we're building a animal pen that has 480 meters of fencing to enclose her pig in the rectangular pen. Seems like a lot of fencing though. So kind of use this diagram. You may not necessarily get this diagram in the future, so kind of be ready. I think we're going to see a lot of this kind of problem, so be ready for that. And then take this function f of x equals 1/2 x squared minus 9x minus 2. Graph that on a graphing calculator or utility or Desmos and find the vertex and x-intercepts. Round everything to the nearest hundredth. Go ahead and pause the video here and work those out. You should have gotten for number 1, y equals, or f of x equals, something like that, negative 1/2 the quantity x plus 2 squared plus 5. And the key to number 2 is in the labeling. You want to do something like x and y to write your constraint equation. 2x plus y equals 480. Solve for the y from there, get into it. You should have ended up with a max area of 28,800 square meters. That should be a big barn and a lot of area for our pig to roam. And lastly, x-intercept should have been negative 0.22, remember those are points. Also 18.22, with a vertex at 9, negative 42.5. Polynomial functions of higher degree. So things that we're looking at here, polynomial functions are continuous, which means essentially you could draw essentially the whole graph without lifting your pencil. No breaks or anything like that. So polynomial functions, smooth and flowing, no breaks, no jumps, doesn't skip anywhere, just keeps going. Not continuous. This is not a polynomial function where it jumps from there to there. They have smooth, rounded turns, no sharp corners. So polynomial. So sketching transformations of monomial functions, we're looking at f of x equals negative x minus 3 to the 6th power. What we would recognize here is the exponent being even. So what that means in terms of shape is it's very similar in shape to our parent function, x squared. So all even polynomial functions like that, they're going to look similar in shape. So we can kind of think of that, and it actually has the same central 3 key points. So if we were just talking about x to the 6th power, we would be talking about negative 1, 1, 0, 0, 1, 1, just like the parent function. Now the rest of the points get stretched, but the 3 key points in the middle there, they would be the same. So we can use that idea, say, well, here would be my vertex at 0, 0. I'm going to shift it right 3, and then instead of our parabola opening upward, it's just going to open downward. So vertex, reflection, and it is parabola in shape, but instead of maybe passing through here like x squared would, that's why it's tighter and narrower as it goes down. G of x equals x to the 5th plus 2. X to the 5th, that being an odd degree there, is going to behave like x cubed, which is one of our parent functions. The x cubed graph with the key points negative 1, negative 1, 0, 0, 1, 1. We are going to shift everything up too. So we're going to do that and have those same key points and similar in shape, but again, kind of the same thing. The higher the exponent goes, kind of the more stretched or vertical it goes. And from Math 3, leading coefficient test with our polynomial function, rise or falls in the manner below. So when our highest exponent, that would be the degree of our polynomial, when it is odd, it's going to start low and end high. We're not sure what happens in the middle, but it's going to start low and end high. Or you can say it falls to the left and rises to the right. And that's as long as our leading coefficient is positive and it therefore has not been reflected. If the leading coefficient is negative, so we have a reflection, instead of starting low and ending high, like the x cubed parent function, it's going to flip, start high, end low, or rises to the left and falls to the right. When our degree is even, it's going to be a lot like x squared parent function. Starts high, ends high. Not sure what's necessarily happening in the middle. We're just talking about the end behavior. Or rises to the left and rises to the right. If our leading coefficient is negative, we do flip that graph. Starts low, ends low, falls to the left, falls to the right for an even degree. Example 2, apply the leading coefficient test to the function f of x equals negative 3x to the 8th minus 4x to the 3rd plus 2. First question, think about it. What is the degree? 8. What is the leading coefficient? Negative 3. Particularly what's important there is that it's negative. The 3 part stretches it, but we're just talking about end behavior. So now combining that information, what's the left hand and right hand behavior of the graph? Even degree, but negative means reflected. Starts low, ends low, or falls to the left and falls to the right. All right, part B. G of x equals 4x to the 5th power minus 3x squared minus 3 halves. What's the degree? 5. What's the leading coefficient? Positive. So we have an odd degree like the x cubed parent function, positive, no reflection, starts low, ends high, or falls to the left, rises to the right. So that's how you answer those. Zeros of the polynomial function. Two statements are true. The function f has at most n real zeros for degree n. We'll get more into that. It has at most degree minus 1 turning points. Turning points means it was going up, now it's coming down. That's a turning point. Also called relative minima or relative maxima. So finding the zeros is an important problem in algebra. There's a strong relationship between graphical and algebraic approaches here. So basically these 4 statements are interchangeable, related. Once you know one, you know the others. So if x equals a is a zero of the function f, then that means that x equals a is a solution of the polynomial equation when it is set equal to 0. Probably most importantly for us, that means that the quantity x minus a being a 0, is a factor of the polynomial function f of x. And then also very important, for the graph, a comma 0 is then an x-intercept. So once you know one, you know the rest of these. Example 3, finding real zeros of a polynomial function. Find all the real zeros of f of x equals 1/2 x to the fourth minus 2x to the third plus 3/2 x squared. Then determine the maximum number of turning points of the graph of the function. Well, one thing I'm noticing is that the fractions here are a little bit, make it kind of confusing. So maybe we take that fraction, like the 1/2, the leading coefficient there, and just factor that out. At the same time, factoring out the 1/2, we can notice that there's also a common factor of x squared. So we have factored out the greatest common factor there. We can continue factoring here, x as a trinomial. So x minus 1 and x minus 3. So the zeros of the function, that's going to net us a 0. Set it equal to 0 and solve. And a 0 and a 0. Zeros are numbers. So 0, 1, and 3 are the zeros. What's the degree? Might want to go back up here. What's the degree? Fourth degree. What is the maximum number of turning points? 1 less than a degree. At most, it could have 3 turning points. And as we continue to help us with the graph, and this does take us back to math 3, the factors like here, exponents and exponents for our factors, the exponent here is the multiplicity of that factor. So the multiplicity of the factor x is 2. The multiplicity here is the invisible exponent of 1, and a multiplicity here of exponent 1. So those multiplicities for the factors are going to tell us what happens when we look at these as x-intercepts. 0, 0, 1, 0, 3, 0. What happens if our multiplicity is odd, like here and here, for the 1 and the 3, the graph is going to cross the x-axis. It's going to like come from below, pass through the x-axis, and go to above. Or come from above, pass through, and go to below. But when the multiplicity is even, like this one, for that 0, x-intercept of 0, 0, it's going to touch the x-axis, but not cross. So I actually like to say it's going to bounce at that point on the x-axis. So if we were going to look at the graph here, we would start with, after we've done that factoring, go ahead and plot those x-intercepts. 0, 0, 1, 0, 3, 0. We would take a look at the end behavior. It was degree 4 with a positive leading coefficient. Starts high, ends high. So I'd probably kind of mark something like it's going to start over here and it's going to end over here. And then what happens at each of these? Well, as we come down at the 0, 0, which came from here, it has an even multiplicity, so it's going to bounce off of that point. And when we bounce, it is rounded. It is not sharp. It is not a basketball bounce. Because remember, we said earlier this is a polynomial function. It has no sharp corners. Everything is smooth and rounded. So now it's coming up. Well, it's got to turn around very quickly to hit here, which has an odd multiplicity. So it is going to pass through or cross the x-axis at that point. We're going to turn back around. This one is going to, again, odd multiplicity, cross. And there's our graph based on the rules of the polynomial and what happens at the zeros based on multiplicity. Example 4, go ahead and sketch. We might need a little bit of extra information to really see what we're looking at here. f of x equals negative x to the fourth plus 3x to the third. Probably want to start by factoring. See, there's a greatest common factor. Since our leading coefficient is negative, we really want to factor that out as well. We will apply the leading coefficient test. So the degree is 4 with a negative leading coefficient. So 4, but flipped. It's going to start low and end low. And since we're going to sketch it, we can just be informal about that. Find the real zeros. That would be by the factoring. So we factored out the negative. I think that's as far as we can go. So we're going to get a 0 here and a 0 here. Those are the factors. Plot those. Notice I did change the scale to by 2. So 0, 0, 3, 0. That may not be enough because we don't really know what else is happening for us to be starting low and ending low. So maybe we plot a few extra points. So we could plug in negative 1. So raise that to the fourth power. 1. Opposite, negative 1 plus 3 times negative 1. So negative 1 and negative 3, that makes negative 4. So we can plot a point there, negative 1 comma negative 4. Definitely going to be interesting to see what's happening here. So if we plug in a 1, negative 1 plus 3 is 2. Probably also good to know what's happening at 2. 2 to the fourth power is 16, so negative 16 plus 3 times 8, so 24 and 16, it's 8. So it goes up quite a bit there. It's going to come back down. At least with those, we have a better idea of what's happening in some of the other places. All right, example 5, or fake example 5. Might not match what you have in the text here. Find a polynomial function with the zeros. So now we know the zeros. We want to go back to and connect to we know a 0. That tells us that we know a factor. That's what we want to use because we want to come up with the factors that will allow us to get to the function itself. So we could say our function f of x, g of x, you can call it whatever you want there, f of x equals, turn this into x minus that, x minus that, x minus that, x minus that. Now it doesn't say these are the only ones, so maybe we have some others, but this is going to be definitely the simplest one that we could use. Now we are going to want to put it in polynomial form, so actually multiply it out. I think our best strategy might be to go here, multiply these two, and then multiply these two. They are difference of squares. So x plus 1 times x minus 1 is going to be x squared minus 1. And these two make x squared minus 9. We multiply that out, x to the fourth minus 1x squared minus another 9x squared plus 9. Write it as f of x equals, there it is in polynomial form. And another one, a little bit more challenging, as now we have some binomial style irrational numbers as our zeros. But same strategy. Part B, f of x or g of x or k of x, whatever, x minus this, x minus this, x minus this. Now when we do these, it does need to be x minus this, so we will need to surround that part in parentheses for grouping perspective. So I'm going to use for these some brackets to say x minus that, and then another factor bracket x minus that one there. So I definitely think we should multiply these together. Before we do that though, I think we may want to regroup this and say group with x minus 2. Put the parentheses there. And same thing over here with the idea though that the minus is going to distribute. So x minus 2 minus root 11, x minus 2 plus root 11. Benefit to doing that is now it's an a minus b, a plus b situation. Difference of squares, we can multiply those together without going through all of the, so if we know that in difference of squares the middle term is going to cancel out. So with this part here, we definitely want to multiply these. We get x minus 2 squared minus the root 11 squared. So we're going to get x squared minus 4x plus 4. Remember, that's x minus 2 times x minus 2, not just squaring both things. So x squared minus 4x plus 4 minus 11. And we can simplify and combine like terms. And then last, to put it all together, x gets distributed to all three. Negative 3 gets distributed to all three. Clean it up. F of x equals x cubed minus 7x squared plus 5x plus 21. That's it for today. See you next time.